top of a non-relational structure, right? In this case, I say JSON, but really what it means is kind of a complex type or an object or a structure, right? So traditionally, SQL has been operating on flat structures, right? Tables, think of Excel, etc. But there's definitely room to advance SQL beyond just that. The challenge right now is that there is no standard for this as well. So a lot of different people are doing their own thing. Some have the advantages over other, in my opinion. So I'll talk to you about one of them that I've been working on. So for those of you who don't know me, I've been around here for a little while. My name's Rahn. I've spent 8 years at Oracle working in the real performance group. And after that, I spent a year and a half working at Cloudera, mostly on the Impala SQL engine there. And then for about the last 2 years, I've been working at a company called Snowflake Computing, which was started by a couple of the architects out of Oracle. So that's kind of what I've been up to. And kind of ironically, a talk on JSON actually gives a little bit in a slide, the data represented as JSON itself. So for those of you who haven't seen JSON or aren't familiar with it, this is basically what it looks like. More formally, JSON is short for JavaScript Object Notation, right? So this is basically, I guess what I would say, the de facto standard of the way things on the internet communicate, pretty much, right? So by that I mean that JSON is structured, not to be confused with this terminology where people say unstructured data, right? So really, if you have unstructured data, to me that's just a pile of bytes, right? JSON is actually self-defining in the sense that, as you saw on the previous slide here, we actually have named fields, right? They aren't necessarily flat, but they are named. And while JavaScript doesn't support all the types that complex languages or SQL data types exist, it does support things like strings, floats, etc. Right? So I would say probably JSON falls more to the category of semi-structured, if you will. But as I mentioned, it certainly is self-defining in that sense. So one of the questions that comes up quite frequently is, how did JSON get to be so popular? So how many people here are working with an application or a data set at their shop that has JSON, right? Does anyone have this? Yeah, a handful of people, right? It's starting definitely to be more prolific. And I think one of the reasons for that, too, is that JavaScript is becoming much more prominent, and to use Mark Andreessen's phrase, on a play on it, that software is eating the world. JavaScript really has probably been eating the world. So much so that Jeff Atwood of Stack Overflow fame once wrote a little blog post and kind of joked about making Atwood's law, which states that any application that can be written in JavaScript will eventually be written in JavaScript. I'm not sure how long ago that was, but definitely there is a lot of JavaScript out there, including a lot of people that work with Node or Node.js, if you will. Right? But really, the prominence of JSON has come from REST APIs, right? So we're living in a world that's connected these days, right? Our phone, Internet of Things, etc. Everything is talking to everything. Like your toaster is sending messages someplace, and something is receiving them. Your meter, your smart meter, is sending up data to somewhere saying, hey, here's these things. And it's really hard not to actually structure that so that the system on the other side can consume that data too, right? So that's why JSON in REST APIs is becoming, I think, very predominant. In addition, people have moved away, at least the smart people that I know, from basic, print line, syslog messages for logging or just, text file logging to a structured log, right? So they're generally structuring those logs with JSON, and the reason is because now you actually have named fields that you can go through and search and load them into something like Elasticsearch, directly. So Elasticsearch, for those who don't know, is kind of like a text search engine, and it can consume JSON natively. And basically, since you have a self-defining structure, it loads it in, and then all of a sudden it says, okay, here's the fields, or facets, if you will, that you can query on, right? And you didn't have to do anything. All you did was load the data. You didn't make a schema definition or anything, because the schema definition kind of came along with the data. And jokingly, Has anyone ever tried to work with XML? You know, definitely those of us who are smarter used to work with XML. But you know, I think JSON is a much cleaner, more humanly readable format. It might not be as expressive as XML, but generally, I think for what most applications or what most use cases are, JSON suffices pretty well. You know, and at the end of the day, there is something to be said for having a self-describing text format because it makes data extremely portable, right? I mean, CSV didn't get to be so popular because it was difficult to use, right? It became popular because any system could ingest a CSV source file, right? Now granted, there are disadvantages for large amounts of CSV. If you want to perform analytics on text, we all know that that's pretty slow. But to make data portable, it definitely is a useful attribute. And of course, portable data is becoming more and more prevalent in today's systems and integrations and integrations because we're bringing in data sets from third parties all the time, right? I just have a few listed here. You know, data.gov. You can pull down stuff. You know, you can pull down weather data in JSON format, right? So if you're doing some discovery, it says, hey, you know, like I had bad sales these days last month. What was the weather like in a certain place, right? So you can go to a public data set, pull that down. Generally, it'll arrive in JSON format, but you have to kind of then put it in the system that you want to run queries against or join it to, right? And if there's a mismatch in data types or format, that kind of becomes difficult. So flexible data models has kind of been on the rise lately, and you know, jokingly, you know, I pulled this off the MongoDB slide or site and kind of made a slide of it. Now, understandably, the argument here is flawed, and that is that the crux of the thing here is MongoDB saying, hey, you need to have flexible schemas, and at Craigslist, when they wanted to add a column to their MySQL table, it was going to run for months, right? Now, unfortunately, this is not a problem with the relational model itself. This is a problem with the implementation in MySQL because many commercial databases have been able to add columns to tables as a metadata-only operations for over a decade, right? It's just when MySQL does it, they make a new empty table, add the column to it, and then they move all the data from the current table to the new table, right? And obviously, you know, for those of you who are, you know, deep mathematicians, you can figure out what the big O on that is, right? You know, not a very scalable operation, right? So, but that said, I think there is value in, you know, thinking and considering flexible data models, right? And it makes things easy, especially for systems that have diverse data, right? So if you think about, you know, applications that are kind of sending payloads back and forth in kind of basic what I refer to as CRUD interactions, right? Create, replace, update, or delete, right? These are kind of just basic, you know, put get type of things, right? Versus kind of like more elaborate analytics or more specific kind of transactional stuff, right? And JSON or document databases, if you will, like Mongo and Cassandra, have become more popular recently because they allow this ease of use, right? It's kind of a developer thing where, hey, I know I can put anything in there, and of course, as with most things, there are trade-offs, but it makes it easy for me to, you know, just put data in my system. I don't have to adjust my system when my data changes right away. I can actually just land it in there, and then when I know what I need to pull out, I can pull it out, right? So there's zero friction going in, but it takes a little bit of knowledge when you pull it out, in that sense. The challenge also with systems like this is that they don't easily support analytics, or even aggregations, if you will, or even SQL, right? So these are basically very low-level put-get type commands, which makes it a little bit difficult, you know, to gather insights from your data in this format. And for example, here's kind of a basic MongoDB working example, right? So we essentially have a table, if you will, called zip codes. And we're trying to figure out all the states that have a population of more than 10 million people, right? So this is essentially how you would write that query, if you will, in MongoDB speak. And then there's a equivalent SQL statement below that, right? Now, obviously, you know, there's probably a little selection bias in this room for the latter, and that's okay. But I think when you think about if you were an analyst or a business analyst or someone who just said, hey, you know, how many people could write the first one versus the second one, right? And then how well could it actually run in the sense that, you have a system basically built for single put get type of operations versus, say, a parallel SQL query engine that can run in a fully distributed mode, right? So I really think, in my opinion, that we're moving toward what I would call a consumption-first model, right? And that, what I mean by that is we're really focused on, for new systems, on getting data in fast and friction-free, right? The vast majority of data being collected and analyzed today is not really transactional data of yesteryear, right? This isn't debit credit all over again in 2015, right? The amount of transactional data that exists out there is, the 1%, I would say, versus the 99% of, big data, right? And by big data, or I guess I would just call it today's data, we're really capturing things like events, activity, things like this, right? They're not transactions per se. And while we want to capture all them, the way that these systems have been built is that they're essentially outputting in a format first, and then put on perhaps like a data bus or written to a file, and then those files get loaded into an analytical system later, right? So they're not going directly into like an RDBMS or some other type of system necessarily, right? But at the same time, we want to get those that data into a system with near zero friction so that we can quickly run analytics on it to help derive value from that data, right? But this also includes the ability to easily deal with evolving schemas without breaking one's current data pipeline, right? I think the goal here is to be agile, not fragile when it comes to dealing with these types of challenges, right? So, for example, how many people here are getting data from a third party, and one day that third party changes the order of the columns in your CSV file, right? And it breaks everything, right? You're like, oh man, now your data didn't come in. Now, consider the fact that if you had self-defining data or self-named data, that the order of the attributes would be irrelevant. It wouldn't matter what order the physical was in the file, because they all just describe themselves. That's kind of what the point is here. And then, kind of moving on, the reality is too that we really do still need schemas, right? But we can apply them in a different place than we used to, many years ago. We can apply them actually after loading and kind of leverage what I would call schema on read techniques, right? So, the image here of a stoplight is in reference to that's kind of a saying I guess I heard once by a friend of mine kind of on Twitter, and reworked just a little bit. Schemas are a hindrance to moving fast the same way that traffic lights are, right? Both are useless when you're the only one on the road or the only one interacting with data, but when you have hundreds or thousands of people accessing that, like, you need a little bit of structure. You need some organization. You need to be able to not just have a free-for-all, right? So with that, I thought, what could an example data pipeline look like, right? So from a modern application, you could do something like this, right? So essentially, we could land the data in S3 or on some other data bus, right? And bring it along somewhere so it gets put on a distributed file system. And from there, we can then load that data into our system that we want to perform analytics on that data on, right? So this is the kind of the important friction-free part, is that we can actually bring the data into a parallel distributed system and be able to interrogate it right away, right? Because it's really hard to interrogate large amounts of data, even on a single machine or a single file system these days, right? So I think it's kind of important to be able to bring that data in and then kind of be able to do a little bit of, I guess what I would call discovery, and then apply a schema, right? So at that point, if we bring data in its raw format, if you will, we can apply schema as a schema on read and then project up the data that we want into a relational format, right? And from there, we can do our refinement and augmentation, right? So we're essentially now into what I would think is common knowledge for ETL or ELT pipelines, right? And then, of course, after that, we can then publish out our data to a set of tables or data mart, etc. And then on top of that, people can run queries and access that data in the same way, shape, or form that they do today, right? So in this case, we're kind of doing ELT with a little bit of emphasis on L, the load part, in raw format, right? So we aren't actually refining our data, but we have full fidelity data coming in. Now, of course, if it were only that easy, right? It always looks good on PowerPoint, but in reality, there are some challenges with that, right? So first, one of the challenges is getting in data into a system without actually defining a schema, right? So, and by a system here, I don't necessarily mean a file system, right? It's really easy to land files, but to be able to operate on those files with engines that can interrogate them at scale is a bit of a challenge, right? And because we're bringing more or less in text fields, we have to be cognizant of the fact that performing analytics on text files, or string fields, if you will, is going to be slow, right? Because these are not optimized binary, formats, right? So, in addition, because most systems have kind of been operating under the premise that all the data looks similar or follows the same model, if the schema varies across different records, if you will, or different objects, that can be challenging for systems as well, right? There are systems that are out there that can bring in data in semi-structured format, but as a result of that, to make things efficient, you also have to include a schema with it. Now, schemas can evolve, etc., but it doesn't do the schema discovery on its own. And of course, again, perhaps a little selection bias here, but I think people really want to be able to perform ANSI SQL on this data and be provided with the necessary extensions and functions to actually interrogate that data easily, right? So, with systems that are out there today, I think there's quite a number of options that one could try. And based on my experiences, I've seen quite a bit, having spent time in both the relational Oracle world, the Hadoop world, and kind of the cloud world now. And that is, probably the first and foremost way that people were processing this data is bringing it into something like HDFS, and then using Hive to access this data. But the way that they did that is they built a SERDI, right? So a SERDI is essentially a shim, a computer program that is able to read JSON and project scalar types. Now, that's nice, but now you're operating A on text files again, which isn't really efficient. And B, as soon as the data changes, now your SERDI is going to break, right? So it becomes brittle and high maintenance. Right? Things like Spark can read in JSON natively and do schema inference, but of course, analytics on text files again is going to be slow. And things like BigQuery can consume JSON as well, but they do require a schema to be built around that when you load the data. Redshift is more of a traditional RDBMS. They have some JSON support, but really what their support is they load data in as text and then give you a handful of functions that may work for your or may not. Right? So these are just some of the examples that are out there, including Snowflake, who I'll talk about in a little bit. So at Snowflake, we were trying to think differently, right? We were thinking, hey, how could we take the best of all the relational world that was out there and all the SQL that people love and use and apply it to a structured data world, right, or a semi-structured data world, and give them the ability to perform analytics on this data without having to do, I guess, what I refer to as gymnastics, right, or text gymnastics, right? So what we built was something kind of interesting. We have native ingest support for semi-structured data, if you will, JSON, Avro, XML, right? So that can be consumed wholesale directly into the system. And there isn't a requirement in Snowflake to define a schema up front. So we kind of solved this because the relational world is built around types, right? There are SQL types, right? A string type, an integer type, things like this, date type. And one of the challenges if you have an object is that an object can be more than one type, right? So we constructed a new data type, which we call variant, right? Which is in essence an any type or an object type, right? So now we satisfy kind of like the relational world side of things by having a type, but that type under the covers can be really anything, right? So a little bit of trickery there, if you will, below the water. And additionally, when you're running analytics on these things, you want it to be in an optimized format. So when we ingest data, we actually use the same optimizations and the same format for if it's relational data, flat data, or if it's structured or semi-structured, right? If it's JSON format. So what I mean by that is that schema discovery is done on load of semi-structured data, and we find repeated attributes in there, which is pretty common. Like most ingests of JSON format are very similar in shape. Now some fields might be missing, or they might have additional fields, but the majority of the payload looks very common, right? For example, if you've looked at something like tweets, right? If you've looked at the REST API from Twitter, things can vary, but for the most part, there's a lot of things that are the same. So on ingest, we actually discover those attributes and then shred them out into columnar format, right? The same columnar format that columnar SQL and engines run on, right? So in that sense, we can apply the same optimizations to both, right? We don't have to have a separate format of storage, and it's not just text, right? So I thought we'd switch gears a little bit and actually move from slides to do some hands-on stuff and pull up, I guess, the scary dark place known as the SQL prompt. Okay, so this will be a little bit challenging because I have to look over my shoulder because I'm doing split screen, but we'll work with it. So here I basically have kind of just a SQL project here in Snowflake, and what I'm going to do is kind of just work through a little hello world, or I guess Scott emp-dep type example, just to give you a little bit of look and feel at what. Right. So I'm just going to use a couple databases. This is just environment stuff, and I'm going to make a one-column table called T, and that table or that column is going to be of type variant, right? So as I mentioned on the earlier slide, we can just create this one-column table, if you will. It's sort of like a JSON table, right? Now in this case, I only have one variant column in the entire table, but variant can be a column with other scalar types as well. But this is just kind of a wholesale type thing. And then what I'm going to do is I'm going to stick one record in here. And so I'll scroll down or back a little bit. So essentially here, you can see this has a lot of different sections in this JSON, right? So we have some scalar values, full name, age, gender. Actually, phone number, area code, and subscriber number are both scalars as well, but they're not at the top level, right? So there's an object called phone number, and in there are two strings, right? In addition, we have a children attribute, and this children is actually an array, right? So the array is denoted by the square brackets if you're not super familiar with JSON. So in this case, we have 3 children, and each one of those 3 children has 3 attributes, name, gender, and age, right? In addition, we have a second array called cities lived, and in cities lived, we have 4 different cities, and then we have an array of the years that this person lived in this city, right? So in this case, the array is just a list of values. It doesn't have a name-value pair, right? So this will kind of let us play with, if you will, a lot of the different structures that appear in JSON, right? So first, after we load this thing into Snowflake, let's just select it back, right? So if we just select star from our table, you can see that all the attributes show up, and it's printed in the screen, very much like it looked when I inserted it, just plain text, but the order is a little different, right? But that doesn't matter because JSON doesn't need to have specific ordering, right? All the fields are named, so it's irrelevant what order they appear, right? So if I had a bunch of JSON where the first attribute was foo and the second one was bar, it is the same as if the first attribute was bar and the second one was foo, right? Because when I ask for a certain attribute, I ask for it by name. So this is stored internally as this variant type as an object now. This is not, despite it being shown to the screen as plain text, it is not text internally. So the extensions, what I'll be showing you next is that in order to traverse into a JSON object, we actually use the column name with a colon to denote the separation between things like database, schema, which are also dots, right? And the JSON path, which is also dot notation as well, right? So in this case, let's bring up the full name. And so for that, I'm just gonna, say select v colon full name from T, right? So we have the column name and then the attribute name as it was appeared in JSON, right? So in there, you can see now I actually have a value back, and that value actually is quoted, right? And that might seem weird. But the reason is because v is a variant and it's an any type. So in this case, the type actually denotes it's a string, and so it's actually quoted. And to kind of make it SQL compliant, if you will, we can take this and we can actually do kind of Postgres style casting, if you will, or we can just do toString or something like this. But for some reason, I seem to use the Postgres style these days. And then we can rename it, or column alias it. And in that case, you get back what you probably are used to, right? From a relational table. You get just a simple text field, right? So that's how easy it can be using just kind of the dot notation, if you will. Now, obviously, there are some other scalars in our data payload here. So as mentioned, we have full name and gender, and then up at the top, I think we have age as well. Age, yeah. So let's pull out full name, age, and gender, all three of them, and let's do some, fancy, cast it to an integer, and gender as a string, right? So now I actually am pulling out scalar values from a single JSON object with SQL. That makes it, relational, if you will, right? So we're bringing back, I guess what I refer to as kind of relational payload here because all our values are scalars. Now, as you can see here, just on the top third of the screen, phone number has two parts to it, which are also scalars. So we can, just pull that out, but the phone number itself is actually an object, right? And that object has two string scalars in it, right? So how do we pull out things that are kind of scalars but one level deep, if you will, right? So for that, we just simply use our dot notation, right? So in this case, I'm using, column name v colon phone number, which is the first level attribute name in JSON, dot area code, which is the second level attribute name, and then I cast that to a string. In this case, I also select the subscriber number. So now it's fairly trivial to actually interrogate a second level scalar, right? So we've done both a top level scalar and a second level scalar. And then if we want, we can kind of put this all together and give you essentially all the information of Johnny Appleseed, his age, gender, area code, and phone number as scalars, right? And this is what I think everyone is used to seeing from a relational table again, right? So I think, as an extension to SQL, again, there is no exact standard for this stuff. This kind of is very intuitive, right? It's not hard for a person to know SQL to necessarily interrogate something that is a complex type or a JSON format, right? So next, we can move on to some more difficult stuff, so dealing with arrays, right? So as you can remember, we have this array of cities lived, right? And so I'll just select that back itself. So here I'm just selecting, cities lived. In this case, cities lived is an array of objects, right? So we're bringing the whole payload here, but I can select that back in SQL. But my response is actually a structure, right? So let's try and access something in this array, right? And for those of you who have programmatic knowledge, accessing things in arrays isn't hard, but let's actually first find out how many elements are in this array, right? So this actually returns, right? So if we want to find out how big that array is, we can use this handy-dandy function on an object that takes an array and say, hey, well, how many elements are in that array, right? So now I know there's 4 elements in that array, right? So that can be of use when you're just calculating the number of things in a list, right? This is kind of synonymous to count star and a group by, right? If you had a totally flat version of this, right? So next, we can just pull out the first element of the array, right? So for those of you who have messed around with stuff like this in Python or any other programmatic language, arrays are zero-based here. So we actually give the field name, cities lived, and then square bracket 0, square bracket. And so now we can actually bring out the sub-object, if you will, from that array. So right now we're bringing the first record of that array out individually, right? Now we can also then take that and kind of dress it up for full SQL, cast it to a string, give it an alias, and now we can pull out just the city name itself, right? So now we have a scalar value of the first city that this person lived in. But probably, it's interesting to get one city, but how do we get all of them, right? Because now we have an array. And how do we return those in kind of a user-friendly format? Well, we could do some gymnastics like this. We could just do a union all, and we know that there's 4 elements because we ran the query on it before. And that works for this type of hello world example. But when you're running this type of interrogation on a larger data set, which you don't know the values of each array, you might not be so successful with this. So what are some other options? Well, we could do, for those of you who are kind of familiar with Postgres, we could use something like this, where we have we select it from the table, and then we do a little generator, or generate a sequence of integers, if you will. So in this case, we're generating 4, and then we're substituting that into the array spot. I have sequence 4 there. That's just a function, basically, to return a sequence. So this runs 4 times, and now we got all 4. But again, we're kind of at the same challenge, right? How do we get this to work at scale and at any size array? So in order to do that, a single record, and we need to return it as 4 different SQL records, right? So we want 4 rows back, if you will, in this case, like we have here, but we don't want to do it, selecting them individually. So what you have here is we have a flatten function. Paste this in here. So you can kind of see on the right-hand side here that the flatten function takes in an array, right? And we use the table keyword to scroll up the screen. We use the table keyword to pass in, or to tell it it's a table function, and we essentially are doing a Cartesian product here, right? So what we're doing is we're taking every value from the left side. In this case, there is only one record, even though that's a structured row. And then for each one of those, we're actually unrolling or unnesting, if you will. That's probably a common term, unnesting, for SQL people. Unnesting that array into records, right? But what you see here, let me make this a little bit smaller. And so we can see all the column headings on top. So we have this list of kind of columns that actually come out of this table function, right? So now we have something kind of interesting. It's not just unrolling and returning some stuff. It's actually unrolling this and giving us a whole bunch of new column names, right? So we have things like a sequence number, which is just essentially a unique value for that record coming out. In this case, the key is null because there isn't a name value pair here. We know the path of the array index, if you will, the bracket 0, etc., which is what we used explicitly. And then we actually have the value itself, right? So now, and then this is actually a reference to the parent that it came from. This is more, typically used like when you have recursive flattening, in this case. So if we just simply simplify our example, and now we actually want the value column here, which contains the payload of cities lived, what we'll do is we'll run this query, which essentially we are selecting tf.value, right? So let me pull this back up just a little bit. So we alias our table name to be, or flatten to be a table alias called TF, and we're taking that special column called value, and we're actually using that. So now you can see we actually are getting the same text more or less that we had on the screen before. We have these 4 objects, but now you'll notice that instead of 1 record containing 4 objects, we have 4 records containing 1 object, right? So we've essentially unrolled that list of 4, 1 list of 4 things, into 4 lists of 1 thing, right? So to kind of take it the next step, we can actually pull out from value. So value is our column name, right? Which is also a variant type. We can then apply our JSON path, and we can pull out, here, let's do this so that it shows up on the screen. There, so now you can actually see the full query. So without the line wrap, so we're selecting table name, TF, column name, value. So we're using our typical database dot notation. Then we have our colon separator, because now we're going to start the JSON path. And then we select city name and cast it to a string, right? And then we select from T, which is our table. And then we pass in, V, which is coming from table T. And then it's an array being passed in. So now we're unrolling an array of 4 things. And then we're selecting an attribute from each one of those 4 things, right? So now, again, we're kind of on the path to transforming something of structured types into a grid or relational type, right? So now we can also do something like adding in the years lived. Now in this case, years lived is still an array, right? So now we essentially get a result. All right. Get back to the right focus. Now we get a scalar London, but now our second column is actually an array of list of values, right? An array of these years, right? So we can kind of think about this and put our SQL. The years that you lived in, that this guy, Johnny Appleseed, lived in Portland, right? So we can actually apply a predicate more or less the same way you would in the relational world, but we use our same type of notation. So we use the table dot column with the colon separator to the attribute name, and then the double colon as a cast. Right? So here we pulled out an array of the 4 years that Johnny Appleseed lived in Portland. Right? So we know there are 4 values, and we can see that by the number of records returned, or the number of records in the array, but we still only have 1 row, if you will, being returned. And we can again use our array size function to see that, sorry, copy and paste failed. Right, so now we can apply array size to years lived, and we get a value of 4 as well. Right? But this is probably this is one way you could do this, but you could also kind of do it a little bit more relationally, if you will, which really isn't a word. But we can then do two levels of flattening, right? Because we have the cities lived array, and now we have the years lived array. Both are arrays. So if we flatten both of them, we kind of can get something that looks like this, right? So here I'm selecting the city name as a scalar string, and then I'm selecting the years lived, and also, which is the array, the second column, and now I have a third, YL, which is years lived, which is the array itself. So now again we get these special columns from our table function that kind of give us the list of values, right? So you can see in the value column here, second from the right, you have the string of each year, right? So we have London appearing 4 times with each element in that array, right? So now we can kind of take that column by itself and cast it, the value column coming out of the years lived flatten, and we can do something like this, right? So we can actually get kind of what you would refer to as kind of like a tabular view of this data, which essentially has the city name and then the year for each one of those, right? So now I've fully flattened a complex structure into a relational, typical relational form, right? Just one more quick example. We can kind of do this as well. So we can apply predicates and do group bys. I use the array size to see how many years I lived in Portland, but now I kind of take the above structure where we have each year and the city repeated for each year, and then do a group by, which is kind of like if you only had a flat table, how you would solve this problem, right? So there's kind of several different ways that you can approach things in integrating and working with JSON, and I think it gives a very intuitive interaction for relational SQL types, right? And I don't mean types, the database type, but types meaning the person type. Okay, so let me switch back to slides. Okay, so just kind of in summary, I hope that was an interesting example, kind of hands-on type thing. I think self-defined being redefined, right? So we have self-defining data that's out there. Really redefine how we work and interact with this data, right? We can have a system that we can land and ingest essentially raw JSON or objects or structures types and bring them in and run SQL on them natively, right? That allows us to build our data pipelines to have both self-defining and predefined schemas, right? So we don't have to choose which one we can have or give up one for the other. We can actually use one when it makes sense and then switch to the other one when it makes sense and give us the best flexibility there. We can have a system that's purposely built from the ground up to run against self-defining and complex data types without being without being fragile, right? We want our system to be agile, but not fragile and brittle and hard to work with, right? So we're taking the best of both of these worlds. So I guess at the end of the day, you can have your JSON and your SQL too. So with that, I'd just like to say thanks. And if anyone has any questions, I'd be happy to take them. Yes?
Yeah, as far as performance implications, so if you have hundreds of millions of rows of records coming in, like indexing, so how does that all work?
So the question was, is if you have hundreds of millions of records coming in, how does indexing and stuff work? Well, with Snowflake in particular, we actually use a lot of metadata to do data elimination. So since it's a system built for analytics and not transactions or point queries, if you will, single records, we do a lot of techniques to leverage that. So if you're thinking that this isn't a substitution for a CRUD system per se, but it is a substitution for trying to run JavaScript MapReduce across a MongoDB cluster, right? In essence, the format that you can export from MongoDB with MongoDB export can be consumed directly into a system like Snowflake, right? So dumping data and bringing it into a system to do analytics on isn't entirely difficult. Yeah. Any other questions? Yes?
Did you, following through with what your example there, did you build a view on top of that table and make it actually look like a table then?
Yeah, so the question is, could you build a view on top of a JSON table, if you will, and make it look like a relational table? Absolutely. And that's one of the tricks that people are doing with our system, is they actually are building what looks to be a relational view, because most of the tools these days, or I should say all of them, know how to deal with that, right? So, but since there is no standard for nested or complex types, essentially no tools can work with those types directly, right? You can type in the SQL and run the SQL, just like I did on the command prompt here, if you can store a query as a report. But if you want to access an object, like as a presentation layer type thing, you can build a view that has that complex and SQL extensions built into it. And then you can use that with anything. Yeah. Any other questions? Yeah.
Can you use it against only MongoDB or like MySQL? Can you use it against MySQL?
So the question is, can you use this against MongoDB or MySQL? So you can. So Snowflake is a separate database management system type thing. It's not a layer to put on top of something, a la say like Spark or one of these other type things, which is only the kind of query execution engine, and you can have different storage engines. Snowflake itself is a complete solution, and that can be consumed as well. Any other questions? Yeah.
Do you have a free version where we can download and play with it?
The question is, do we have a free version of it? The answer is kind of yes, but to download and play with it, the answer is actually no, because it's actually delivered as a full database as a service in the cloud. So all you need is an internet connection, and talk to one of our guys on our sales team, and they can set you up with a kickoff. So it's pretty easy to get started. So, okay, if anyone else has any other questions, just grab me, and I'll be happy to answer them. Thanks again.